Hello, my name is Ayron Gors, and this is my project for presentation for CE570. So for this week's project, we were tasked with defining area Jacobians for each of our external surfaces of a body of our choosing, and my body of choosing is still my silo. So this image here is my lines of code that define my hollow cylinder, and you can see the added lines of code for the area Jacobian there towards the bottom, being R1 for the inside surface, R2 for the outside surface, and R for the bottom surface, as well as the definition of my unit vectors and my scalar field for my surface body. These are the lines of code that define my hollow hemisphere that sits on top of my hollow cylinder to make up my silo. And as you can see, I added the lines of code there for the area Jacobian for the different exposed surfaces. So I have an inside exposed surface and an outside exposed surface. And the only difference between the two will just be the radius. As you can see, I've defined it as R1 squared times sine t, R2 squared times sine t for the inside and outside surfaces respectively, as well as I have defined the unit normal vectors for the inside and outside surfaces you can see there, which I'll be getting into in a later slide, as well as the definition of my scalar field, which won't be checked this week per the instructions. These are the plots that MATLAB outputted. As you can see in that left image there is my plot parameterization of my silo shape, and you can see all the different individual exposed surfaces. And then on the right image there is my scalar field, and you can see the heat map plotted over my scalar field equation of x1 squared plus x2 times x3. So now I'd like to highlight my hand verified area calculations for each of my shapes. So starting with my cylinder here, you can see my body parameterization in that top equation there, as well as my three total exposed surfaces, the inside, outside, and bottom. And starting with my inner surface, you can see that my area Jacobian is defined by the magnitude of the cross product between the partial derivative of my body parameterization with respect to theta and with respect to z. And the reason why those two variables are chosen is because for my inside surface, you can see that my radius will be constantly held at 4. So doing the math out there, you can see that my area Jacobian comes out to R1, and taking the double integral of that will give me my surface area of that inside surface to be 502.655. And moving on to my outer surface, you can see that it is the same exact equation and process as my inner surface, only now my radius is updated because my outside surface has a larger radius. And doing the math out there, you can see my result to be 628.319. And then for the bottom surface, you can see that the partial derivatives now are taken with respect to r and theta because my height is not changing, so that is technically constant, but my radius will change between r1 and r2 as well as the orientation theta. And doing my area Jacobian for that results in a value of r, and taking the double integral of that gives me a total value of 28.274 for that bottom surface. Moving on to my hollow hemisphere, you can see that I have two exposed surfaces, an inside and outside surface, as well as the definition of my parameterization at the top there. So finding my Jacobian area, I knew that I had to take the partial derivative with respect to phi and theta because my radiuses are held constant depending on which surface I am trying to find the surface area of. And working through my math there, you can see that my end result for my Jacobian area is r squared sine phi. And taking the double integral of that with respect to the inside surface, so r1 equals 4, results in a value of 100.531. And taking the double integral with respect to that area Jacobian, but now updating the radius to 5, gives me a result of 157.08. Here you can see my calculated area compared to my MATLAB output. You can see the MATLAB output is 1,416.858 in the top there, and my total calculated area that I did by hand was 1,416.859, which are extremely close, so I know my code is working correctly, as well as you can see the other outputs that MATLAB gave me, such as the flux and the volume of the body that I've verified. And finally, I'd just like to highlight the definition of my unit normal vectors for all of my different exposed surfaces. And in that top equation there, you can see that's the definition of the unit normal vector. And all of that information I've actually calculated previously, like the area Jacobian and the cross product of the derivatives. So as you can see, for my inner surface, I got a normal vector of negative cosine theta, negative sine theta 0, and a positive equivalent for the outside surface of the cylinder, and then a 0, 0, negative 1 for the bottom surface of the cylinder since it's oriented downwards. And then finally for the hemisphere, I got two normal unit vectors that are equivalent but changing in sign to be dependent on the inside and outside surface of sine phi times cosine theta, cosine phi times sine phi, and sine phi times cosine theta. So thank you for watching.